Start. Okay, good morning everyone. So today we are going to look at data mining. So yesterday we looked at data, how data is represented, what are the different types of analysis one can perform. And then we also looked at how data is managed in a file system in a database management. So today we are going to look at the data mining landscape. Now, I should warn you that there is a lot of work that is done in data mining right from the 1960s. So there is no way we are going to cover all of that. So what I'm going to do is to give you highlights of what is data mining, why it is important, what we should be careful about while doing mining, and what are the important things that you need to take into account. So that's what we are going to do. So data mining is also known as knowledge discovery. And yesterday somebody was asking, what is the difference between querying and data mining? Hopefully you will get an answer today. And if you still don't get an answer today, come and talk to me. I will try to explain. So this one, the key in business is to know something that nobody else knows. So then you have a competitive edge, and that is how it got started. So keep that in mind. So here is a motivation for traditional training. How do you find these guys? There are 10 billion records on 10 million customers in the main database. With all this information we have about our customers and all the calls made, this is from a telephone company. Can't you just take the database to figure out which lines have been set up temporarily and exhibited similar calling patterns in the same time periods? The information is in there, I just know it. So this is what is the expectation. So what is the difficulty with this? The difficulty is finding similar problems just described is very hard. So similar is not exact. So similar is something that has to be defined in some way, and it may vary from domain to domain, context to context, and place to place. So find similar problem is very hard. Who should be given incentive? So in a company, there is always this decision making. Who should be given incentive, and then managers or somebody makes decision based upon various factors that are associated with that. Now it's very difficult to quantify them in a query. How can we group usage patterns into similar groups? How can we say this pattern is similar to this pattern, but not the same? And there are multiple patterns that are different from each other. Should we approve the purchase by this credit card by this user? This is one of the problems American Express card tackled in the early 70s, because that is the only card that did at that time real-time approval of credit without having to check anything. And they had a expert system to do that, which is similar to data mining. So why? Massive amounts of data, more and more online data stored, web corporate database. Challenge is real-time versus post-point. So this is important to understand. Some problems need to be solved in real time, and some problems is not necessarily need to be solved in real time. For example, if you are talking about cyber attacks and other things, you want to be able to do it in real time. If you are monitoring for air quality, water quality, and other things, you want to be doing it in real time. But there are situations where you can do after the fact analysis for understanding what has happened. So if you have, for example, valet footage or footage of some other place, then you can analyze that. So there is a difference between post-mortem analysis, which is also called forensic analysis, and real-time analysis. So no easy way to describe what to look for. This is the key. If there was an easy way to describe, then we could formulate it as a query. There is no easy way to describe because it changes from domain to domain, context to context, and what you are trying to do. This is the real problem. Traditional interactive query-based approaches fail because you can only extract information, but you cannot see what the groups of patterns are. Size of data, different purposes, need for domain knowledge, all of these become relevant. So data mining is part of the knowledge discovery process carried out to extract valid patterns and relationships in very large data sets. So certainly you should understand why and how this is different from query processing or even search. Usually don't know what to look for, like a voyage into the unknown, regarded as knowledge discovery or learning from basic facts and data. And this has roots in AI and statistics. As you know, today there is more and more of AI, machine learning, neural networks, and a lot of statistics that is being used. Uses techniques from machine learning, pattern recognition, statistics, databases, visualization. So I want you to clearly understand that data management, data querying, report generation is different from data mining. In data mining, many times you do not know what you are looking for. You want to figure out what the data contains before you know what to ask for. This is true in association rule mining, this is true in clustering, this is also to some extent true in classification. So what to do? A few months before the contract expires, this is with respect to ISP phones I was talking about, if we can predict which customers are likely to quit. So remember we talked about predictive analysis. Here you need to predict which customers are likely to quit, then give incentive to those who are likely to quit. Don't do anything for those who are not likely to quit. So the question is, so because they don't want to give incentive to every user, right? That becomes too expensive, too costly. So they really need to understand who is likely to quit and who is not likely to quit or switch. Then they want to target them. So this is known as target marketing. So most of the target marketing, like some of the mails you get for, we'll give you a credit card, apply, you have been selected for this and all. They're all target marketing generated by mining algorithms based upon your characteristics, your income, household income, for example, your spending pattern, your age group, your demographics, whether you are a male or a female, what kind of things you buy. All those things come into picture to determine whether you are a target for pushing a particular credit card on you and making you buy that. So the main problem in data mining is how do I predict this behavior and corporate palm reading. We are very familiar with palm reading and horoscopes, human intuition, and data mining, knowledge discovery in databases, that is known as KDD. There's a whole conference devoted to KDD today, and it has been going on for the last 15 years. So this is the basic problem, I hope. How did the current avatar of data mining come about? It did not happen overnight. Mining has been around for a while. As I said earlier, people have been looking at samples and examples. There was something called example-based reasoning. So there has been a lot of work on. So earlier, humans and earlier work focused on looking at a few representative samples and try to generalize from them. That is what still humans do. But computers cannot do that. Computers don't know how to generalize from small set of samples. That is why we use very large amounts of data when you are doing mining in an automated manner, because larger amount of data is much easier to recognize patterns. So enablers, what are the enablers? Cost of storage. So earlier you could not store a lot. Remember I showed you disks that had 5 megabytes with a fridge sized disk. Today you can hold that in your pen drive. reduced cost of processing. Machines have become faster. Perhaps you remember Moore's law, that every 12 months the CPU processing doubles. Ability to store, process, and manage large volumes of data, databases, data warehouses, and internet. New techniques such as association rules I mentioned for market basket analysis, sequence data processing, ontology, stream data processing, information fusion. However, the biggest problem is scalability, understanding or interpreting the result, which is part of visualization, variety of data you have to deal with, filtering very large outputs are new and important issues. So these are the challenges in this domain. So what are the technological advances that gave rise to this? One is increase in processing capabilities. Second is advances in storage technology. And then increase in network capability, reliability, speed, and all those things. This is also one of the things that has contributed to cloud computing, which we will see in the next lecture. So all these together came together to facilitate data mining, application of statistical machine learning algorithms, systems plus architecture. So although this was being done on a small scale, doing it on a large scale was not possible earlier. So these technologies and software developments facilitated that. Right? So this is typically what is considered traditional data mining. You have some data. It may be loan data. Suppose say you are working in a bank and you are applying loans. So how do you determine whether an applicant who has applied for a loan is a worthy candidate for approving the loan? So that is something for which you have to predict. So from the data description, you can do a bunch of different things. I have just listed a few things like clustering, classification, association rule mining, anomaly detection, regression, subgraph mining, and then you get the final results, and somebody has to interpret the final results and use that in a particular way. So this is how we were doing traditional data mining, and for each of them we had different algorithms, different packages, different way of looking at the data, and then analyzing. So in data mining, a domain expert assists the analyst to determine the best mining. So this is important. If you are giving a loan, you need to understand some of the details of how a bank performs, what kind of loan you should be given, and what kind of return you can expect and all those things. If it is classification, it's a different thing. So for example, for direct marketing, typically classification is used. Interpretation of results is the most difficult and important. So I want to emphasize this because it is not just a question of running a package and outputting the result. Somebody needs to understand the results and sort of see whether it makes sense or not. Not in every case it will make sense. Sometimes the results are counterintuitive. You never thought about this, but when you see that, you think, haha, this is possible, and I can understand how this is possible and do that. So there is that aha moment in exploration and knowledge discovery, which is sort of not present in query. So applications, these are the applications that are customer profiling, which is finding new customers. So if I am selling a product, how do I target who I should approach for buying that particular thing? So that can be done using customer profiling because I have lots of data from the past buyers. So I have plenty of data from the past buyers and now can use all that data to determine who could be the current buyer. So remember today, irrespective of what you do, even if you buy a small thing, immediately you get a survey. Why do they ask for that survey? Exactly for data mining. So they will ask you for your gender, your location, your income level, and your household information and all that. All of them contribute to target marketing. market basket analysis. So I mentioned this, we're not going to, this is a big thing, Walmart and D-Mart kind of things do that. Amazon being an online thing, it doesn't have to do that, right? Because there is no placement of objects next to each other. You don't walk through the aisles, look for this or look for that. Managing inventory, so that is part of managing risk analysis. So for insurance companies, use this risk analysis, whether to give you an insurance or how much to charge for your insurance if you are a high risk. Insurance, loan, stock, text analysis, library, web, fraud detection, this is very important. Customer relationship marketing, scientific discovery, forecasting, etc. So all of these applications have been benefited by data mining, earlier data mining techniques. Any questions? So what is data mining? So this is very important. The next two slides, I'm going to ask you some questions, and I want your answers to get an understanding of how you understand data mining. So to understand data mining clearly, one needs to differentiate between two concepts. The first concept is the notion of causality. I'm sure most of you are familiar with the notion of causality. And second, the notion of correlation. So correlation is a mathematical or statistical thing that you are also perhaps familiar with. So it's very important to understand these two and also the differences between these two in order to appreciate and understand data mining. So one is based on semantics. So causality is based upon semantics. Causality means one follows the other. If this happens, then I know this will happen. So that is cause and effect. Whereas that is based upon semantics and intuition. Whereas correlation is not based upon semantics and intuition. It is based upon how data patterns fit together. So you take different sets of data and see what kind of relationship exists between them. So that can be quantified mathematically, whereas causality is much more difficult to quantify. So what is data mining trying to do between these two? So here is your understanding. So what is causality? So we understand this as cause and effect. Heavy rains means flooding. So there is a cause, there is an effect. Flooding will not happen without heavy rains. So there is a cause and effect that we understand. What is correlation? Correlation is different. It's a mutual relationship or connection between two or more things and their strength. So you can see that as temperatures goes up, ice cream sales goes up. So these are two independent things, right? So you can track the increase in temperature, you can track the increase in ice cream sales and see whether there is a correlation. Is that true? So that is correlation. So if you understand this clearly, if not, ask me. I'm going to ask you a couple of questions. So in correlation, you can also have positive and negative correlation. That means this corresponds to, so you can say if it is winter, maybe ice cream sales will go down. That's a negative correlation. But if you go to European countries, actually ice cream sales go up in winter. So that's a different thing. It depends upon the context. Here, people drink hot water in winter. There, people drink cold water in winter. So there are differences. That depends upon the data set, where the data set comes from. So, do the above two mean the same thing? That is the first question. Are these two same or different? Is causality the same as correlation?
No.
This is the litmus test for whether you understand data mining or not. All of you have taken a course in data mining? Yes? No? Maybe? Forgotten? Long time ago? Anybody?
So these two are different, totally different. So these two terms are totally different.
They are different. You're absolutely right. These are different. So we need to understand why. Now, important to understand why. So which of the two we want to identify in mining? So when we do mining, do we want to infer causality or do we want to infer correlation?
Correlation.
Huh?
Correlation.
No. See the underlying thing. What do we want to infer? Do we want to infer causality or do we want to infer correlation?
We need to infer causality.
Huh?
We need to infer the
causality.
Which one?
Causality.
Causality. You're right. So we want to infer causality, but that's what we want to infer. Which one does mining actually identify?
Correlation.
Correlation. Why? Why can't we identify causality? But we also know that correlation does not necessarily imply causality. We know that. But causality implies correlation. But correlation may imply causality, may not imply causality. That is the best we can do. This is also the reason why we need domain understanding or domain expert to understand. So the reason, let me see, so why? Why is that? Okay, so this is something I show. I don't know whether it will come up. If I click on it, can you click on that link?
Try clicking on the touch screen.
Can I do that here?
Yeah.
Is there internet here?
Yes.
Ah. So I don't know whether it will have gone. Ah, okay. So here are some examples. There is a website called Spurious Correlations. So look at this. I'm not going to show you everything. Look at this. Popularity of the dumb ways to die meme correlates with the number of electronics engineers in Utah. This is a strong correlation, but this is not causality. So this is what you need to understand. Just by looking at correlation, you cannot conclude that dumb ways of dying follows electronic engineers in Utah. Similarly, I won't show many things. So here, okay, so liquefied petroleum gas usage in Spain correlates with assistant professor salaries in the US. So I really want you to understand this, because even though we determine correlation, because we have a mathematical way to determine correlation, we don't have a mathematical way to determine causality. So we determine correlation, but you should not conclude only based on correlation that there is a cause and effect between them. That is where the domain understanding and domain expertise comes into picture. Anybody can look at this and say, this does not make sense. But number-wise, data-wise, it makes a lot of sense. There's a strong correlation, but causality is not there. Okay, so how do I go back to my original slide? Okay, so do you understand now? Causality is a more intuitive semantics concept. Correlation is a mathematically defined concept. It's easy to calculate correlation. It's very difficult to calculate causality. So what we do is, most of the mining algorithms do find the correlation, and from then we try to map it into causality. This is very, very, very important to understand what mining is. So, I said what mining is. Now, what is not data mining? Is there something called data mining, or everything is data mining? Data warehousing is not data mining. Data warehousing, when you ask OLAP queries, it's a query. You formulate the query and you get the answer. Ad hoc OLTP, online transaction processing, is also not data mining, because you formulate a query, whereas in data mining, there is no query formulated. Online OLAP aggregation, summary, data visualization, agents, mediators. So don't confuse buzzwords. You know, there is a lot of buzzwords floating around and people are confused between what is this versus what is that versus what is that. So don't get search, look up, they are not mining. So here is another brain teaser. So this is purely my opinion. Are there things data mining is not likely to do? If so, what kind of things are they? Today, with AI and ChatGPT and LLMs, we have a tendency to think it will do everything. It can do everything. But I personally think we are still a very long way from some of the things. It can do a lot of things, no question about it, no doubt about it. It's very useful. I use it in many situations. But there are things that are beyond the purview of that. So let us take an example. Data mining cannot substitute for human intuition and generalization capability. Humans are capable of taking very few small examples and generalizing. Computers cannot do it. You know, machine learning algorithms cannot do it. They require very large amounts of data to figure out things. Have to wait and see where ChatGPT takes us. I don't think DM systems will discover. So I was in a workshop with physicists. All of them were renowned physicists, and I asked them this question. Can data mining discover equal to MC squared? And their thinking was, no, it cannot. This is not something that is purely data-driven. This is based upon human intuition, human faculty and understanding, and various understanding which may or may not reflected in the, and we don't even know what data to look at. Similarly, there is a famous formula in chemistry, PV is equal to RT. Gravity, Newton's laws of motion. Newton did not go and look at 10,000 apples falling every day to determine gravity. It just occurred to me in an instance when he looked at one of them. So it's not the question of looking at very large amount of data and generalizing and concluding. Okay? It may discover new black holes. So here is the difference. You can collect a lot of data. These are being done. Like I told you about the God particle the other day. God particle was sort of, there was a conjecture, but there was no proof. There was no experimental result to say that. And that came from the Hadron Collider. Similarly, you know, things like black holes and all which are again, all of these are proposed and then experimentally verified. Remember I talked about two ways of independently verifying things. And this is also true for equal to MC square. I should tell you this anecdote. I know I may exceed the time, but this is interesting. So Einstein published his paper on equal to MC square, but there was no way to verify it. It was completely theory, and he proved it and showed it. So the problem was, it was not an experiment that you could set up in the laboratory. They had to wait for 2 years for a full solar eclipse to verify his theory. So 2 years after the publication of his journal paper, not him, all other scientists, some of them agreed with his theory, some of them did not agree with theory, went and collected data for a full solar eclipse to determine whether the theory was correct or not, and it turned out to be perfectly correct. So this is the difference. He was able to formulate it even without looking at any data. The data came 2 years later. So people traveled to different places on Earth where that eclipse was visible, collected the data, and then matched it with this formula, and it was correct. So this is the difference between what we can do with computers and what we can do with human ingenuity. The value of pi perhaps can be determined because if you look at a large number of values, diameter and circumference, you can get a generalization. Okay, so much for that. So I hope you understand the underpinnings of what data mining is and why it is different from what was being done till then, and what it produces. It produces a different thing that we don't know many times. So data mining tracks, prediction, descriptive methods, use some variables to predict unknown or future variables. So this is very important. This is, it will come. Descriptive methods, we talked about it, find human interpretable patterns, and this one, types of data. So this is the other thing that you should understand and remember. There are 3 types of data mining. One is supervised. What is supervised? As the name says, driven by known information about data. We call it labeled data. So what is an example? A good example that you can understand is weather, right? For weather, we have a lot of good data. Once the day is over, we know exactly what happened, right? And we have all the parameters, temperature, wind, humidity, sun or cloud or whatever it is. So we have years and years worth of accurate labeled data. This was the variables, this is the outcome. These are the variables, this is the outcome. So the question is, can we use that data to predict future weather? So if I know the weather for the last 1 year, can I predict tomorrow's weather? So that is what is supervised learning. So you use the existing correct data. By the way, we call this ground truth. This labeled data is known as the ground truth. So you use this data to derive a model. And you use that model to data that you don't know. This is also true for target marketing. So if a company sells newspapers or magazines, they have a lot of people who are buying them, right? They have all the demographic information on them. So they know who buy that. Now if a new customer comes, they can match it with that one and see whether he is likely to buy it or not. So in situations where you have labeled data, ground truth information, this is a very effective technique. Classifications essentially is based upon this. optimize existing solution and markets. So that is one form of them. But there are other things where we don't have this kind of data. Suppose say you are given a bunch of points and you say, I want to cluster them. We don't know them, how they cluster. This is also true for graph mining, we'll see that. This is also true for market basket analysis. We don't have any ground truth. We don't have any information, but still we will be able to derive information. So driven by no known or labeled information about data. That's why it's called unsupervised. This is truly exploration, figuring out something that we do not know. And relevance, finding new patterns that may be counterintuitive, relies on domain knowledge to validate. Finally, there is something called semi-supervised, driven by small amounts of labeled data and large amounts of unlabeled data. So this is also becoming very popular. There is also something called self-supervised, where it tries to create its own labeled data set in the process of doing things. And all of these techniques are used in different places in different ways. So sample DM approaches. So classification is one of them. I will not go into the details of that. There's a whole set of papers, but you know what it is. So this is a supervised approach. Why? You take labeled data and create a decision tree. And you use that decision tree for unseen data. And if the model is correct, your result will be correct. If the model is not correct, it will not be correct. So that's what this is. Clustering. Clustering is typically unsupervised because we don't know. Given a pattern, we don't know how many clusters are there. So we may say, okay, identify 3 clusters, then it will identify 3 clusters. If you say identify 4 clusters, it will identify 4 clusters. Association rules. This is, by this time you should know, nobody is answering, so I'm not asking. Unsupervised. Text classification, typically it is supervised because you have a lot of information that you can use as labeled data. Anomaly detection, supervised or unsupervised? Unsupervised. Graph mining, this can be both supervised or unsupervised. You can give some positive and negative samples and then ask it to do inference, or if you don't have any samples, then it will do other kind of inferences and so on. Neural networks, supervised, unsupervised. If you are into AI, you should know this. Typically, neural networks are supervised. You have to fine tune the weights and back propagation, for example, in order to make sure that it gives correct results on lots of labeled data so that you can rely on it for unlabeled data. Deep learning, same thing, can be both self-supervised as well. Big data analytics, it can be both descriptive, prescriptive. This is what you will be doing most of the time. If you become a data analyst, if your goal is to become a data analyst or a researcher, you really need to fully understand this. Okay. So, a lot of people think data mining are just algorithms. So there are various algorithms, clustering algorithm, classification algorithm, association. But it is not. You need to understand that there is a whole life cycle. You start with the data. It doesn't matter where the data resides. It may be in a database or outside. Then you have to do a lot of selection. As I said earlier, not all pieces of data are needed for all mining purposes. So you have to identify which data is relevant, which is not relevant, and then you have to do some pre-processing. there may be incomplete data, there can be null values, there can be values that are not properly done. So you have to fix those things, and then you go to data mining. And then you have to do analysis. Once you do the analysis, it is not necessary that you get the final result. You may have to rethink and go back and change a few things. So this is an iterative process. Data mining is typically an iterative process, not a single shot process. It is not that you get your answers the first time and the correct answer. So this is important to understand. So there are different kinds of models. Some models are better than others in terms of understandability, in terms of accuracy. They range from easy to understand to how do I interpret results. So here is just a spectrum. Decision trees are easy to understand. They can be cast into if-then-else rules. It is easy to understand by humans. At the other end of the spectrum are neural networks that are very difficult to understand. You know you are getting the correct results, but you don't know why. And it's very difficult to explain what is happening in between, especially if you have multiple layers of neural networks. So that is something that you're, and other things, 10 nearest neighbor rules, other things following. Using a model. So you can have a qualitative model, gives the analyst an understanding of the rules. If 35 age is greater than 35 and less than by, then buy expensive cars. Assume you have made enough money, you are willing to buy cars. But now with all the inflation and uncertainty, you may change that to if age is greater than 25 and 35, then trade your expensive car to an average car. So this can be a different rule. Interaction with the model and visualization is important. Quantitative, it's an automated process. Classification, scoring, so essentially you get a score. You get a probabilistic value or you get a confidence. They'll say this can be the case with this confidence. So higher the confidence, the better it is. The lower the confidence, not so good. So how do you test a model? Suppose say you have generated a model using supervised data. So when you generate a model, you always generate a model using supervised data. And this shows briefly, so here is the data that is used for training. And then this is the new data. So historical training data, from this data you generate a model, and then you test that model to make sure that, so you train with some data and you test with some other data. From the labeled data, both from the, because you know the answer here and you know whether this model will be correct or not, that will give you the accuracy of the model. Then you use it on the unseen data. If the accuracy is high, then you are confident that it can be used on the unseen data. But doing this kind of model testing, just using one piece of trained data is not enough. So that's why we have what is known as, K cross validation, 10K cross validation, 5K cross validation. So what you do is you take the labeled data, divided it into K parts, use one part for training, use all other parts except that for testing. Then you train with this part, do the same thing. You train with this, so if you do that, then you can get an average accuracy of the model. So cross-validation is very important to make sure your model produces the kind of accuracy that you are interested in. So application of statistics techniques have been waiting for technology to catch up. The reason I say is that before the automated use of large data, scientists were still doing sampling. Sampling is a very important concept, especially random sampling. It's very important, so you can take a very large data. If you don't have the processing capability, or if you want to look at it manually, you can take a representative random sample and work on it to understand it. So that's what I tell my students to do, even if they are doing very large data. Don't start with a very large data. Take a small sample that you can understand, you can figure out what is going on. Run it with the same algorithm, see what you get. Once you are convinced that it is working correctly on a random representative sample, then you are more confident that the result. So this is part of the sanity check. Remember I mentioned sanity check and validation. So cross-validation is part of the validation, and doing it on a small sample is part of the sanity check. So statistics have been good data mining, the intelligent application of statistical process, emphasis on scalability, handle large data. So the move from sampling to automated things came about because of the processing speed, because of the increase in data, because you wanted to deal with real data rather than small set of data. So classification can be done using neural networks, decision trees, GIAN, base classification, support vector machines, clustering, prediction, association rules. There are a lot of algorithms, time series analysis, text filtering. This is what I was trying to indicate the other day. It is not just one algorithm that you can use all the time. It's a toolbox. So the important thing here is how do you choose your tools for the problem at hand. You know, a few years ago, I visited a company in Bangalore, and they said, sir, you know, we have tie-up with an American company and we have lots and lots of data, and they want us to do these things and we are doing it. So I asked him, how are you doing it? He said, sir, you know, we have 25 different algorithms. We just run each algorithm on the same data set and see what it gives. I felt that this was the wrong approach. You just don't exhaustively run all the algorithms on data set, then how will you decide which one is good? So it is not enough to have large amounts of algorithms that you can apply. Anybody can apply. An undergraduate can run the program, feed the data, you get the result. But then what? So people don't think about it. People only think about, hey, my program ran, it gives an output, so it should be correct. If the program runs, that means it is syntactically correct, not semantically correct. It may be giving wrong results. So keep that in mind every time you write a program. Metrics for performance evaluation. Focus on the predictive capability of a model rather than how fast it takes. Efficiency is important, but accuracy to me is more important than efficiency. So what is the accuracy of a model? How do we quantify it? So here are a few examples. Suppose we have a model, we have created a model and a test data set. We have 1000 test data points, and we know because it is labeled data, 550 are actually correct, yes, 450 are no. This we know. Now we run this test data set on the model and get its output. Suppose the model predicts 500 instead of 550 as correct, and 100 instead of 450 as not correct. So what do we understand from this? How can we figure out something about this model? It is giving some correct answers, some incorrect answers. So how do we figure out? And in order to do that, there is something called a confusion matrix. You might have heard of a confusion matrix. So this is what is typically used. So in order to use that, you have to understand four things. What is a true positive? Data points that are labeled as positive, that are predicted as positive. They are true positive, means they were correct in the label, they were correct in the prediction. True negatives are also important. They were negative in the label and predicted as such in the label. But here we only have 500 out of 550, 100 out of 450. So what happens to the rest? The rest becomes false positives and false negatives. So what is a false positive? Data points labeled as negative that are predicted as positive. So that is a false positive. False negative is data points labeled as positive that are predicted as negative. Okay? So if you understand this, what we want is these two. These are errors. So we represent this in a confusion matrix like this. This is the actual label. This is the predicted class. So in this data set where we had 1000 data, 550 were actually yes, 450 were actually no, only 500 were detected as true positive, 100 was detected as true negative, 350 as false positive, 50 as false negative. So these are incorrect. So how do we compute the accuracy of this model? So the formula that is typically used is this one. This is a very simple formula. Take the correct ones, divided by the total. So here, 500 plus 100 divided by 1000.6. So what it means is, this model is accurate only 60% of the times. 40% of the times it does not give correct results. Now we want this accuracy to be, when is this accuracy 1? Under what conditions is this accuracy 1? When this becomes 0 and this becomes 0. If these two are 0, numerator equal to denominator, accuracy is 1. So that's what you want. But these errors, the more the errors, the less the accuracy. Okay? So why is accuracy so good? So here you can see that there is a disparity between, not so good, disparity between higher number of false positives that will pull down the accuracy. Either this or this will pull down the accuracy. FP is high. If FP reduces to 100, then the accuracy becomes 0.85. And if both of them become 0, accuracy becomes 1. So here is another, so this is more or less what we call a balanced data. Why is this balanced? Because the yes and no are more or less in balance, the equal amounts. Slightly different, but equal amounts. In this data, they are imbalanced. There are 2,450 test data. 2,000 are yes, 450 are no. So there is an imbalance between these two. And you do the same thing, and then you compute, the accuracy is 0.244. So you see that, some models that may give better accuracy for balanced data may or may not be able to give good accuracy for imbalanced data. What contributed to low accuracy? Mainly the large amount of false negatives and also this. Another imbalanced data, 2100 data, 2000 yes, 100 no. Here is the distribution. Now you can see that these two are relatively low and hence the accuracy is very high. So it depends upon the generated model, depends on the representativeness of, this is very important. This is the reason why we do 10 cross-validation. Because if you just take one set, 1/10 of that, it may not be balanced. When you do this cross-validation, you will see that some of them will give high accuracy, some of them will give low accuracy, mainly because of the non-representativeness of the data. Imbalanced data sets are common in medical, security and other fields, so you need to deal with that. Same imbalanced data with a different approach. 2100 data, 2000 is same as before. Suppose I throw away my model and I say yes to all of them and 0 to none of them. If you do that, the accuracy is very high. So this is a problem, right? I'm not even using a model, I'm just, because it's imbalanced, by choosing which ones to say yes and which to say no, I can achieve high accuracy. So this also means that this accuracy equation, this accuracy model may not be very good, may not be correct. It may be good for balanced data, but it may not be very good for imbalanced data. So what is the problem with this approach? A single measure of accuracy does not seem to tell the whole story. So because of that, they have introduced, another thing that you need to take into account is the cost. What is the cost of correct prediction and what is the cost of incorrect prediction? Okay, that's very important. Especially in some fields, you are classifying a patient as having a disease or not having a disease. Cost of classifying a patient who does not have a disease is having a disease is one thing. That's an incorrect prediction. Cost of classifying a person with a disease not having one. The question is, which one is worse? A may be acceptable if there is a simple, inexpensive test to confirm that. On the other hand, B is not acceptable. The cost is too high. Somebody has a disease, but you have said you don't have a disease. That person goes away and dies after a few months. So this is what you have to deal with in real world data. Okay, it's not just playing with numbers. You have to deal with the impact of what these models give you in real world. So, in order to, same for crime, putting someone away for 10, 20 years if there is no crime committed because some model predicted that he was a criminal. The legal matters, student grades, you don't want to give a wrong grade. Stock market, if you make a blunder in stock market, you lose all the money. How can we include cost in addition to accuracy? So there is a cost matrix. So you can associate a cost. You can associate a low cost or a high cost depending upon the semantics. This cost is not fixed. This cost varies from domain to domain and the impact of the error. So here, for example, For this one, there is a very high cost, which is the other one we talked about. And you can now compute cost-based accuracy. So accuracy is 60%, cost is 4900, accuracy is 70%, cost is 8950. Then you have to determine which model is better and why. Is cost more important or is accuracy more important? That may depend upon the domain. So again, these are all ways of looking at what we should do, but somebody has to make decision. The mining system is not going to make this system. This is what I want you to understand. There has to be a human in the loop to make decisions along the way, even if you automate things. It will only output numbers. You have to interpret that and see whether it makes sense. Which classifier would you choose and why? Do you want low accuracy, low cost, high accuracy, high cost? Cost versus accuracy. So I'm going to skip a couple of these like this. You can look at it. I want to get into, so this is important. So there are two additional notions in addition to accuracy, which are called recall and precision. Recall says what proportion of positive values does the model capture. So this is this value over this plus this. So all of them have been predicted. So this was true, but has been predicted as no. So this is the recall. So it only was able to recall TP out of TP plus Fn. Precision is this way. What portion of positive values are correct? So TP is correct across TP and FP. This was also is a false positive shown as correct, but it's actually not correct. So precision is this one. So there are two notions of thing. So recall and precision. Again, when you do mining, you not only compute accuracy, you also need to calculate recall and precision. Sometimes, if the recall is very high, no, I just have a few more slides, finish it off.
Third lecture,
Huh?
Is it third lecture or fourth chapter?
This is the,
Okay.
the fourth may be a little bit short, so together. There are a few more slides, I'll wrap it up, this module.
No,
Okay, that's,
you can continue it after 2 to 2. So we can just talk
That's fine.
whatever it is.
that's fine. I'm okay.
Okay. Continues, then you might have
Yeah.
like,
No, that's okay, we'll break.
okay, let's take a break, okay? Tea is outside this hall, please join us for a tea. Come on.
So again, welcome back. So we've been discussing recall and precision. Now these are conditional probabilities. You might remember. This is the conditional probability of S when it is actually yes, yes when it is no, yes, yes, no, no. So they correspond to these things. So recall and precision are quite useful. So the question is, now we have accuracy, now we have recall, now we have precision. We know that we want recall to be high, we want precision to be high. Recall is 1 when this is 0, precision is 1 when this is 0, as usual. But they may not be 0 at the same time, they may be different. So the question is, can we reduce precision and recall to a single number instead of two different values? How should we combine them? So is it possible to combine? So there are different ways of combining them. You can use arithmetic mean, you can use geometric mean, you can use harmonic mean. So it turns out that, so this is the same thing. So it turns out that arithmetic mean is not good. Geometric mean is also not good for that. So note that recall is 1 for max when Fn is 0. Note precision is 1. What we want is for both to be high. When both are 1, the model is perfect. Arithmetic mean will not work well at the end points 0, 0 and 1, 1 as 0 and 1 correctly. We also want it to be low when 1 is 0. So mean is not appropriate. So mean, if you use the mean, this is what you get, and this is not what we want. So we use the harmonic mean, which gives rise to this guy. So this fits what we want for recall and precision better than the arithmetic mean, because you see this is a curve where it is 0 here, and 1, 1, whereas this one is not 0 here, this has a different value. So arithmetic mean will not give you a good evaluation of recall and precision. So looks for harmony in numbers. So harmonic math does this. So that's what we use. So when you do data mining, when you develop new algorithms, when you do all these things, you compute recall and precision. You also compute F1 score, which gives a combined information about your recall and precision. If both recall and precision are 1, your accuracy will be 1. If one of them is low, then it will not give you a very low value. So F1 score is defined as 2 times precision into recall divided by precision plus recall. F1 score for 0, 0 is 0. F1 score for 1, 1 is 1. F1 score for 0, 1 is 0, not 0.5 as in arithmetic mean. F1 score for 1, 0 is 0, not 0.5. So this is the main difference between using arithmetic mean and harmonic mean. So harmonic mean models recall and precision much better to what we want rather than arithmetic. So this is again another issue you guys as students have to keep in mind. There is a tendency to fit the first known formula. The first known formula may not be the best formula. So you really need to look at which formula is better and why. Be able to justify your formulas and then use it rather than just picking one formula without understanding whether it is appropriate or not. So this is a common mistake that is typically done. So F1 score gives equal weight to both measures. 1 in F1 indicates equal unit weight, so that's what it is. Can be customized by using a beta instead of 1. There is also this notion of ROC curve. I'm not going to spend a lot of time on that. So this is known as the receiver operating curve from communications for historic reasons. But this is another way to evaluate your model, whether your model is good or not. So ROC curve gives an area under the curve. If you have a 45-degree line, that means it is neutral. If you have a curve that is on the other side of that, then you have more area under the curve, and then that is better than that. So that is something that you should look it up. For the example discussed earlier, compute recall precision and F1 score and compare with accuracy. So F1 score is not the same as accuracy. F1 score is considered a better way to do that. So if you look at papers, almost all papers will give you F1 score and precision and recall, not so much of the accuracy. Accuracy is okay when you are dealing with something like Jaccard coefficient, where the accuracy is very clear, either 0 or 1 or the range between 0 and 1. So Jaccard coefficient and you can also use NMI, refined NMI and all those things, but for this one, this is a better way of doing it. And the general formula is as follows. So where instead of 1 you are using beta, so combined measure that assesses precision recall trade-off is F measure weighted harmonic mean. If you substitute beta equal to 1, you get the previous formula. People usually use balanced F1 measure with beta equal to 1 or alpha equal to F. Harmonic mean is a conservative average C. So this is, so if you, so again we come back to this slide where sort of we are, so we did this, we are here. So to summarize, technology, computation speed, fast, cheap and large storage has moved many of these approaches into mainstream age. So, companies today can mine their complete data. Earlier they were mining 3 months of data, now they can mine 3 years worth of data. Soon they want to do mine 10 years worth of data. So the intuition or the understanding is, if you have large amounts of real data, that is better than samples. Samples will be a representative sample, but not actual data. So most of the mining is today being done, like I said, on market basket data, where you're using terabytes of data to do that. And then you want to look for patterns. Can now be applied on actual data set instead of samples. Clickstream analysis. So when you buy something on Amazon or when you go to Netflix, you see a lot of stuff, right? You see, okay, oh, if you like this, you may also like these things. Where does it come from? That comes from what we call clickstream analysis. So every click you make in every purchase is stored. And then from that they compute. So this is a good example of real-time data mining, right? If Amazon shows you that information 15 minutes after you buy, you don't care. It's useless. It has to be shown immediately when you are buying something, so that you are tempted to buy other things. So clickstream analysis is being done. So imagine Amazon is using millions, I have millions of users, billions of items are bought and sold, and then they do the clickstream analysis on that for every user. So it's a personalized target marketing. It is not a general target marketing, it is for you. Same is true for recommendation systems. When you go to Netflix, it recommends you movies based upon your profile and what others who have similar profile have seen. It is not a general purpose profile. Again, this has to be done in real time. It cannot be done as a post-mortem analysis. So how do they do that? So what they do is they use the data to compute and keep lot of information which is matched at runtime in real time. It is not that they do entire data mining in real time. It is still not possible to do that. So they cull out lot of information, like they group people who have similar interests, who have similar things, and then the lookup that they do in real time is much smaller than the amount of information they have already derived from the large amount of information they have. So that's very important. We will also address data filtering aggregation in stream data. We will not be doing stream data analysis. So this brings us to the end of lecture 3. So we need to load lecture 4. So now we switch gears, and in this lecture 4 we'll be talking about big data and cloud computing. Okay, I may edit that other thing. So what I want you to take away from this lecture is, that there are a lot of buzzwords, right? There is big data, there is cloud computing, there is MapReduce, there is this, there is that. And what I see among students is a lot of confusion. They confuse one with the other. Is big data same as cloud, or is it different from cloud? It is not very clear to many people as to what it is. So in this talk, I am going to discuss what is big data and what is cloud. Two separate things. They are not the same. I don't want you to confuse, and why they came about. What was the evolutionary process through which cloud and big data came out, and what kind of things that are happening in that. We are doing a lot of research in big data analysis. We are also doing a lot of research in not cloud computing, but MapReduce and Spark for scalability. So the last two lectures will discuss MapReduce and scalability issues for some of the algorithms that we use. So the question is, we had DBMSs, they were working fine, they were managing large amount of data. What did we do? Why did we do more? So here is a slide that says DBMSs have served as enterprise data storage and management for more than 40 years. Mainly OLTP. OLTP means online transaction processing, which is different from OLAP, this online analytical processing. So typically OLAP is used in the context of data warehouses. OLTP is used in the context of relational DBMSs. So then came data warehouses have provided additional drill down and OLAP that has been integrated with. So the capability of OLAP was not present in the traditional DBMSs. They could not do three-dimensional analysis. They could not do a lot of different kinds of analysis that are possible with OLAP. Then data mining does a different thing. Data mining has also been applied on DBMS data and data warehouses. Remember, I gave the example of the DB miner, which IBM developed. However, data and processing needs have evolved since the advent of relational database. That is what is giving rise to big data. We'll see. Scalability is important, and we will look at data scalability and processing scalability. Two different ways of scalability, and why DBMSs were not very good at these things and why one had to develop it. Especially data distribution, query optimization, concurrency and recovery is very complicated and difficult in multiprocessor system. That is why you don't see DBMSs working with very large number of processors. We do have DBMSs on 8 processors, 16 processors and 32, but you don't see them on 1,000 processors or 10,000 processors, which is a very different ballgame. So scalability, when we come to scalability, you can think of two things. One is the data scalability is accommodated by adding disks and larger disks. So if your data increases tenfold, instead of keeping 1 year worth of data, if you want to keep 10 years worth of data, you need more disks. Now adding disks may be easy, putting data on that may be easy, but processing them is complicated. If you use the same disk I/O for 2 disks versus 10 disks, then you slow down. Your performance will suffer. And you also have to determine which relation should go on which disk, how do you partition it. So there are a lot of complications with that. So this means long wait for I/O given the same number of processors. To overcome this impedance mismatch, you need more I/O throughput, additional I/O bandwidth. This has not been easy. Data partitioning and it need to be figured out. So, doing horizontal scalability using a DBMS is not straightforward. It's fairly complicated. So, because of that, other means like MapReduce has been developed. We will not discuss it in this lecture today, but we will discuss it in the subsequent lectures in this course. Then there is the computing scalability. This means I am adding more processors, or I am adding more powerful processors. Now, it's one thing to add powerful processors, and it's a different thing to feed data to those processors. So remember, in a DBMS, you have to stage data from disk to main memory in order to do processing, and that is the bottleneck. Memory is in milliseconds, processing data in memory is in nanoseconds. So there is a difference of 1 million times, and that is the big problem that one is facing today, because our disks are very slow. We have very large disks, we can put a lot of data, but you cannot do any processing on a disk. Any processing has to be done in memory, which means you have to bring the data, process it, and put it back on the disk. So that I/O is not increasing with Moore's law. It is not doubling every 12 months. It's a much slower thing. Now there is a solution on the horizon, that is the SSD, solid state disks. Solid state disks are much faster. Why? Can anybody tell me why solid state disks are much faster than HDD, hard disk drives? You should know it. You know SSD, you know HDD, but you know why one is better than the other. Anybody? What happens in a HDD?
We use cylinders.
Can you use the mic?
There's a stack of disks, and for every search of data, we have to go track by track, and every disk by disk, and then track, and then particular sector to fetch particular data.
Yes.
This is what happens in SDD, but I'm not sure about how SSD works.
Well, what you're saying is true, but I think the underlying reason is hard disk is a mechanical device. The platter, even today, if you have a laptop without SSD, there is a disk that rotates at 7,000 RPM or 10,000 RPM or 15,000 RPM. That is the limitation. The limitation is the mechanical device. You cannot make it rotate faster and keep the accuracy of data flow. Yes, sector and all those things are there, but the basic reason is that it is a mechanical device which has to rotate. So now compare the rotation of a jet engine, which rotates at about 40,000 RPM, whereas a disk rotates at about 10,000 RPM, and they have not been able to increase the rotation speed. That is the real bottleneck. Whereas in a solid state device, there is no mechanical part. There is no mechanical part. So in the absence of a mechanical part, this mechanical equation is taken away. There is no rotating disk. You can access things much faster. So SSD is faster for one reason, that there are no moving parts. But they are very expensive right now. They are very expensive, and there are certain limitations. For example, in an SSD, there is a limit on the number of read and writes. It's about 2 million or 3 million, but still there is limitation because at the end of that, it won't function. So there is a lot of work done in the database area moving from HDD to STD. So how can we improve the database performance, efficiency, storage when we use STD versus HDD? That's a big research area today because SSDs are going to be here. They are going to become cheaper as volume increases, and then lots of people will, my laptop has 2 terabytes of SSD, which is very fast, but it's very expensive. So you cannot afford a lot of disk space, and hence still a lot of data is stored on HDD. Okay, so understand the basic difference. So when you increase the computing speed, the bottleneck remains the same. The processor can process faster, but data is not flowing. It is like a 3-lane highway merging into single lane. Then there is a backlog. So then it has to wait. It has to wait for the data to come. So this is the real problem which we call impedance mismatch. So we are going from traditional databases to big data. So this is just a picture I wanted to put. This is not a fully correct picture because I say it clearly, it is not just about the size. We'll see what it is. It is about the diversity of data. It's about holistic analysis. These are very different from what we are doing. Certainly the size is big. You need more processing. You need more processing power and other things, but the size is not the only thing. So then what is it? So this is how big data is characterized today. They are known as 4 V's. Volume, velocity, variety, and veracity. So these 4 characteristics define what is big data. This is how it started. Today, I have seen in the literature people are adding anything that starts with a V. They are adding variability, validity, vulnerability, volatility, blah, blah, blah. But I do think that these are the basic fundamental differences. So what are these? Volume. Volume is the size. Now we know how to deal with volume. I mean, databases deal with terabytes of data, so we are capable of dealing with volume independently. What is velocity? Velocity is the rate at which data is being generated. So this can be from sensors, which is sending every 30 seconds data 24/7. You're monitoring various things, battlefield monitoring, infrastructure monitoring, environment monitoring, whatever it is. It is also true for things like Facebook and Twitter. In Twitter, whatever the opinion or sentiment that is analyzed is only valid for 15 minutes. Afterwards, there is a new sentiment because data is changing constantly. So we know how to deal with this because we have developed something called stream data processing system. I have done some research, and we have done a lot of research where you can process data that is coming in at a very fast rate. Now remember, processing data with velocity is very different from processing data in a DBMS. Here, the assumption is data doesn't change. I mean, it changes but very slowly. So if you take a university database, it changes every semester, but it doesn't change every second. So you don't have the same kind of quality of service requirements as you need for velocity. So there are systems today that have been designed and built. They are known as single pass algorithms that deal with stream data. So battlefield management is a good example where a soldier wears 20 to 25 sensors on his body. These sensors continuously transmit different information, his pulse, his heart rate, his hydration situation, whether he is standing vertically or he is not standing vertically, whether his gait is slow or not. Now, if you have 50,000 soldiers, each with 20 sensors, and each of them are sending information every 30 seconds, imagine the amount of data you are going to get. And how do you process that? So you want to detect whether somebody is fatigued on the battlefield so that you can remove that person immediately. You want to identify people close to him who are not fatigued. So stream data processing is a very useful. This can also be useful for highway traffic. For example, if there is a traffic congestion, it can detect traffic congestion and reroute traffic, for example. It can be used. It is also similar for brittle traffic. So we know how to deal with velocity separately. Come to variety. What is variety? Right now we have been dealing only with comma separated data, numeric data, tabular data. But we have images, we have audio, we have video, we have EKG, we have various other kinds of data. That is variety. Now we know how to process each of them individually. There is a lot of work in image processing, there is a lot of work in video processing, there is a lot of work in identifying cancer in various MRI scans. We know how to do it individually. Velocity is something little bit more complicated. Velocity means how good is the data, confidence in the data. It is not that every data is equally good. I mean, a good example is the CIA data or espionage data. So there you get a lot. There is something called human intelligence, and this human intelligence comes from various sources, and the confidence in the human intelligence depends upon the source. How good is the source? What is the track record of the source? So that's very important. So there is work in probabilistic databases, statistical databases, where you assign a confidence to the value you have in the database, and then you do computations or same SQL query computations, and then you also derive a confidence for the result. So if you use data with different types of confidence, what will be the confidence of the resulting solution that you are seeking in that query? So what is important to understand is we now know today how to deal with each one of them separately. But big data analysis says that we want to do all of that together. So a good example for that is a healthcare issue. So if you take it, the healthcare, so you have a person's demographic information, you have a person's pathology reports, you have a person's x-rays, you have EKG, you have various videos, colonoscopy, this, that, scans. Now you need all of that to understand what is happening in this person. Even today it is not done that way because doctors do not have access to all the information about a patient. They have fragmented, partial information about a parent. So they make judgments based upon that. But that may not be completely correct because they don't have all the information. But if you have all the information, then you can do something called personalized healthcare. And then if you have this data for the whole community, then you can also do aggregate analysis for community. You can find out which age groups have a high incidence of this particular thing, or which ethnic groups have high incidence of this thing. All those analyses are possible if you have all types of data and you are able to process them together as a whole, not piecemeal, not individually. Okay, this is the challenge of big data analysis. So, is it clear? I made myself clear. What is the difference between what we are doing today versus what big data and big data analysis is? So, big data analysis is a process of inspecting, cleaning, transforming and modeling large amount of disparate data. That means different types of data, with the goal of discovering useful information, suggesting conclusions and support. So this is what we call holistic analysis. Instead of individual analysis, you want to do analysis together on all the data, and that is why it is called holistic analysis. Of course, there is connection to data mining. It is not very different from data mining, except the details, the data types are different. So analytics include both data analysis and communication. Analytics is not so much concerned with individual analysis, but with the entire methodology. So this is what you need to understand as to what big data is, what big data analysis is. So big data is just a collection of different types of data that are together as a whole, and then analysis on them now has to be done across the data, not vertically. So where do you get big data? I have already mentioned Hadron Collider. It was initially generating 10 petabytes per year, and it was supposed to generate 1000 petabytes and in 10 years. It has been more than 10 years. 2,500 physicists are collaborating in analyzing that data. These are the people who found the boson or the God particle. Large Synoptic Survey Telescope, again large amounts of data. This is another telescope which is used by the US Air Force, generates large amount of data, satellite images, metadata, other information. It also comes from commercial sources. You have billions of camera images, video uploads, web usages and other things. You have YouTube, you have other things. So today there is a push. We are also doing some research on big data analysis, and as we have done on individual things. So there is also large amount of dollar value associated with various sectors. US healthcare, Europe public sector administration, global personal location data, USGS, utility manufacturing. So the big picture is, this is sort of my view. So now, remember I showed you an earlier picture with a similar inverted triangle. There we were feeding raw data, one type of data. Now into the same box, we are feeding structured data, image data, video, audio data, unstructured data. Now you have to generate inferences using all of them, not just one of them. This is the real challenge of big data analysis. And it is not easy, and we are nowhere near it at this point in time. A lot of people are working on bits and pieces, are trying to figure out what model is useful for this, what kind of techniques and algorithms you want to use. So there is a whole science, what kind of abstractions are useful, machine learning, neural networks, what kind of analytics are useful, video processing, stream processing, communities, hubs. We'll see a little bit of, so my view of big data analysis and science. And here are the, what I call, so instead of deriving it, like in mining, we were either doing classification or doing clustering or doing GIAN. Here, there are analysis expectations. You may want to ask different types of questions, not necessarily questions because you cannot write a query for that, but this is what I want to get out of this. Is it possible? Not everything you want to get out of that may be possible. We may not have the algorithms to produce it or algorithms to compute it, but this is the big picture. I also want to emphasize that the result of that, you make decisions, real world decisions, real decisions that needs to be very important. You are also looking at trends and predictions. You are extracting knowledge, you want to understand the knowledge. Visualization becomes very important. Not just deriving 1000 numbers. So this is what, to me, big data and big data analysis is. Trying to figure out a holistic way, transforming instead of one piece of data or one type of data, multiple types of data into actionable knowledge and decisions. So again, data science today tries to do something similar, just like the one I showed for the mining. You can see that for data science, in addition to other things, you have different components. You have computer science, machine learning, mathematics, statistics, probability, software, powerful software, business or application usage. All of this have to come together to perform data science, data analysis or big data analysis. And this is the key. Now, I think there is hope that we are at a point where all of these things, like we say, the stars are aligned and you may be able to do something that one could not do earlier. So just to give you an understanding of what is it. So we started a data science program, a master's in data science program at UTA 3 or 4 years ago. And I was involved in this. I was involved in the development of the courses for that. I also taught one course for 2 or 3 semesters, and now others are teaching that. It's going very well. There's a lot of interest. So we take students from multiple domains. So the key in data science is that you can analyze data from any discipline. I have had students from mechanical engineering, aerospace engineering, biology, social sciences, and electrical engineering, because everyone needs to do data analysis. Their data sets are different, the domain knowledge is different, but analysis is common. Analysis doesn't change much, slightly maybe, not very much. So it's very important in a data science program that you have people from different backgrounds, because they can go back to their domain and apply data analysis in their domain. A computer science person may not be the right person to go apply data analysis in a biology domain, because you don't have much understanding of biology. So that's very important. So data science or analysis is not new. Data collection, storage, management, query search, all of them. Emphasis was on understanding and managing data. Now data mining brought an exploratory and discovery component, first on samples, later on real world data. Now we are combining all aspects of application, business with CA statistics to holistic knowledge. So again, it's not a single approach or a single solution. There is no silver bullet. In my view, using extending current approaches and developing new ones, a suite of approaches, if you will, for modeling and analyzing a diverse complex set is important. So, if you want to define the problem in what you are given and what you want, what is given is a complex data set, maybe from different types of data, and a set of analysis objectives, and what you need to do is determine modeling, what abstractions are needed, what kind of analysis methods are needed, and what kind of visualizations are needed. So this is the problem, this is the approach that you want to use for solving that. And I stress modeling because many times we have this tendency to go from data to applying algorithms directly. But you don't know how it works. So always, just like we use, I don't know if you are familiar with entity relationship diagram, for example, it's a model that will allow you to disambiguate a lot of things in your specification and then translate that in an algorithmic way into a schema that you want to process on. So some intermediate representation modeling, it doesn't have to be ER diagram, it can be a graph, it can be a multi-layer network. We'll see some of them later. So that brings us to the big data analysis. Now you may have a question on what is the difference between mining and big data analysis. So here is my view of the difference between that. In mining, you are taking a data set, a specific data set, and applying a specific mining algorithm, and then getting the result. Whereas here, it's much more broader. It's much more broader. You have data set description, but these are from an application of different types, analysis objectives. You use a model, maybe we have done some work in ER to MLM, so I have put it there. So you need a model, and then you generate analysis expressions, you compute analysis expressions, you drill down, and you visualize. So this is the complete life cycle, including knowledge engineering, deriving data, and then going to modeling, analysis, expressing the objectives, and visualization. So this is what I think differentiates traditional mining from big data analysis. Any questions? No? Okay. So I may have this later. So let's come to the cloud. So what is cloud and what is cloud computing? Again, as I said, don't confuse between these two. These two are not the same. So this came about around 2000, evolved from grid computing with improvements. So we had grid computing, we had cluster computing. By the time cluster computing, server farms, and use of commodity components had become commonplace. So this is very important. So this commodity component. So now both grid computing and cluster computing became a reality only because of commodity components. What do I mean by commodity components? So this was pioneered by one of the computer science faculty from Berkeley. And commodity components is, so remember I showed you disks which were very huge, very expensive. At some point, this guy said, this doesn't look right. Can we produce disks on a smaller scale that are like commodities, like you can buy it cheaply, and even if they are not as good, it doesn't matter because I can buy lots of them, and even if some of them fail, it's okay. So today in a cluster, you may have thousands of disks, and then RAID was invented to make sure data is not lost. Even if there is a failure, single disk failure, you can recover the entire data. So commodity disks, commodity components made grid computing and cluster computing possible, which was not possible before. Improvements and advances in hardware and software, networking was more robust, and bandwidth kept increasing. So I don't know how many of you have used modems. We had modems at some point in time. We were calling up a server with a dial-up modem with a baud rate of 56K, and then they were sending text data across the wire, across the telephone wire, and processing it. And due to internet accessibility, fluctuations of access usage became much larger. we'll come to that. So what is the path to cloud computing? We started with mainframes, I showed you. You can actually think of this as primitive cloud computing where you are not accessing it on the web. You are going physically to a computing center which had a very powerful computer and getting your job done. Today that's what you do on a cloud, but you don't do it over the network. You do it over the web. You don't have to go anywhere. You don't even know what is in the cloud. Then came desktop and PC revolution in the 80s. Then came high performance computing and supercomputers. So you might have heard of, CDC and Cray computers. They were very expensive and they were being used. Then came the internet. After this, because of the internet and the network robustness, came grid and cluster computing. Then came cloud computing. So what is the need for cloud computing? Why is cloud computing touted as the solution, and what was the problem? So here is an example. Consider the official Wimbledon site. Most of you or all of you should be familiar with Wimbledon. This site gets extremely high traffic in the 2 to 3 weeks when the championship happens. For this 2-week period, the site will have high server usage. For the rest of the year, the site will have low traffic and hence most of the resources it's idle. So this was the real problem. In order to serve 2 weeks in a year, you had to maintain all the equipment, all the infrastructure for 1 whole year, paying the cost, bearing the cost. Spare capacity need to be maintained or leased from somewhere. So there is a lot of spare capacity, right? Because you provide resources for the peak demand. But when the peak demand is not in peak, most of the resources are idle. And spare capacity need to be maintained. Or you have to obtain it from somewhere. This is what is called internet scale elasticity, meaning you want the flexibility to fluctuate between high demand and low demand, not wanting to maintain the same level of cost. This was also true for companies, IT companies. They were maintaining a lot of equipment and they were not being utilized. The traditional approach is to keep enough spare capacity to deal with the needs of 2-3 weeks. It's expensive. Hardware gets old and obsolete. As you know, in our world, 2 years is too long. You need to replace hardware every 2 years, and then you have to replace software. Hardware gets obsolete. Maintain and manage people, software acquisition and maintenance. It was not easy or possible to outsource this just for 2 weeks. So there was no ways to say, can I outsource this, my Wimbledon site, for 2 weeks when there is peak demand. It was not just IT shops were maintained that were quite expensive. So this was the situation. So the question is, what is the solution to this situation? These situations and needs were a side effect of internet availability and ubiquitous storage. So this demand for Wimbledon servers was mainly because of the internet, right? When there was no internet, people were reading newspapers. Millions of people were not looking at the site. So internet created this problem of easy access, immediate access, 24/7 access. And that had to be maintained. Making things available on the web was critical. Enterprises were maintaining expensive IT shops with all the costs and headaches that came with that. So cloud computing became the answer for that. So how did it become the answer? Could not be done earlier due to technological limitations. So this is also very important to understand. As I said, sometimes our expectations move faster than what technology can provide. It doesn't happen. Technology has to catch up with that. So reliable networking, large bandwidth, management of clusters, privacy, software as a service. So all of them had to come together in order to make cloud happen. So what are the components of a cloud computing environment? There are 4 components. First one is what we call thin clients, or clients with a thick swing switch. I'll come back to that. Second component is the grid computing. What is grid computing? Ability to connect disparate commodity computers to form one large infrastructure harnessing unused resources. This is important and very much required. Today, you know AWS, you know Azure, you know what Google provides. They all provide this capability. These two were already there. These are not new. These two are new. Very specific to cloud computing and very different from what we were doing before. What are they? Utility computing. Paying for what you use on shared servers like you pay for public utility such as electricity, gas and water. This was not the case before. You could not go and rent a server and say, I want it for 2 days. I'll only pay for 2 days. That was not the case. So in cloud computing, this is one characteristic. So you can rent, and like electricity, gas and water, so when you turn on electricity, you don't go and ask anybody, should I turn off my air conditioner? You don't ask, right? You just turn it off. You assume that somebody is willing to provide that. And that is on-demand resource provisioning. You can demand resources at any time you want without prior intimation. You can say, I want 100 computers. Okay, that's not enough. I want to increase it to 500 computers. You don't have to tell anybody. It will be made available to you automatically in this environment. And that is the difference. Whereas in earlier, IT shops were localized. Every company maintained their own IT shop. Somebody else's IT shop could not access your IT shop, even if it was idle. That was not allowed. So these are the characteristics. Utility computing, on demand, is not static, no need to indicate resource requirements ahead, ability to add and remove computing resources. I'm saying resources, it can be network bandwidth, it can be software, it can be hardware, it can be disk, it can be anything. Not just CPU. So what is thin client? I don't know whether some of you may be aware of what a thin client is. So when we used to communicate with the server on a modem, we had what is known as a dumb terminal. I don't know whether any of you have heard of a dumb terminal. It was really a dumb terminal in the sense that it had no processing capacity. It would only transmit information to the server and then put the information that it got from the server back on the screen. That's all it was doing. But today, we don't have dumb terminals. But that's why I put with a thick switch. So your laptop can act as a dumb terminal. In fact, that's how you use your laptop when you access the web. Your laptop is not doing anything. Everything is done at the other end. It is just sending information for display. And your laptop is displaying, or your tablet, or whatever it is. So you don't even need a powerful machine for cloud computing. You just need a device which can interface with the server, and if you want graphics and other things, yes, you need more powerful machines. Grid computing, this is also not new. This has been around, but it has been pooled in such a way to make utility computing on demand possible. Any questions? So I'll just explain what a thin client is, so I'll skip this. I have also explained grid client. So grid client was used for a very long time. Especially people from other disciplines, physicists, people who are doing genome work and other things, they needed very large amounts of computing for cancer research and other things. So grid computing was very popular at some point. In fact, at some point, some of the researchers would even ask, hey, are you willing to donate your laptop or desktop time when you are not using it so we can use it and do some computation? And that was also going on. Another example is, for example, mathematicians are very fond of computing the next prime number. Now, they have computed prime numbers up to maybe 300 digits now. We don't know how many digits the next prime number is, but that computation is very expensive because you have to keep checking every number. So all those things require tremendous amounts of resources. That's why grid computer and Condor, other things came into picture. And the important point is pay as you use. Pay as you use is a concept that we used only for utilities, water, gas, electricity, not for computing. Now, this is just a historical perspective. For those of you who may be aware, Sun is no longer a company. It was acquired by Oracle, but it was a very big company at some point in time. At some point was shipping servers with extra CPUs that could be brought into use as needed. You would not be paying for them until you use them. So they would send you a machine with 16 CPUs. You can today turn on only 2 CPU and pay only for 2 CPU. Later, if the demand increased, you can turn on 2 more CPUs and pay for them. So this is a very primitive way of pay per use. Cloud is a generalization of that. Cloud supports pay as you go for individual components such as CPU storage. So here is a diagram about the relationship of supercomputers, distributed system grid. So here is one. There are lots of definitions of what a cloud computing is. Cloud computing has the following character: the illusion of infinite computing resources. That means you can get any amount of resources you want. You don't have to own it. The elimination of upfront commitment from cloud users. This is on-demand provisioning. The ability to pay for use as needed, pay-per-use provision. So cloud computing makes computer infrastructure and service available on demand, on need, or on demand basis, like utilities. The computing infrastructure could include anything: hard disk, development platform, database, computing power, complete software. To access resources from the cloud, vendor organizations do not need to make any large-scale expenditure. This is very important. So, there is something that we call what is called the leveling the playing field. The difficulty for smaller companies earlier, apart from IBM, Microsoft and others, was entering into the market. They had to spend a lot of capital expenditures to set up IT shops. Now with the advent of cloud, all of that disappeared. Anybody could rent the minimum number of resources you need in a very cheap way. So organizations need to pay per use. That is, organizations need to pay only as much for the computing as they use. The billing model of cloud is similar to that. So there is a vendor, there is an organization which is the user. So this is important to understand. In the traditional IT, if somebody is a business management here, they will understand there are two kinds of costs. Fixed costs and variable costs. Fixed costs are also known as capital expenditure. Like for example, building this auditorium is a capital expenditure, one-time expenditure. But maintaining this auditorium on a daily basis is variable cost, operational expenses. So in an IT company, you have both of these. And unlike this auditorium, which is going to be here for a long time, computers don't last for a long time. They have to incur fixed costs every 3 years. Now with cloud computing, this whole fixed cost is eliminated. There is no fixed cost. You just rent. So if NIT allows people to come and rent this auditorium, it becomes a cloud computing example. They can come and rent it for a week, conduct their seminar, pay NIT and go. You can easily convert it into cloud computing and make money. So coming back to our Wimbledon applications, in general, the usage of computing that can be increased or reduced on need basis is called elastic computing. So computing requirement varies. So this elastic computing capability is provided by cloud. Now, Wimbledon can just lease 100 CPUs for 2 weeks and then reduce it to 2 CPUs. So the total cost is reduced. So some of the applications, Hotmail, for those of you who may be familiar, was launched in 1996. It is widely considered as the first cloud computing application, even though cloud computing itself became popular a little bit later. The data is stored at the vendor servers and users could pay incrementally to increase disk space. Google still has that model for increasing the disk usage, also known as leveling the playing field or barriers to entry. So cloud computing has really removed barriers for entry to the marketplace. Twitter, MySpace is gone. Wikipedia, YouTube, Facebook, LinkedIn, Google, everything today can be seen as cloud application. Companies that provide hosting services are also cloud services. Perhaps Salesforce.com is one of the best examples of cloud computing usage. Started in 1999, they only use cloud. Everything they do is on the cloud, there is nothing else. They are very good at customer relationship marketing. CRM company was the first successful example of providing software as a service in the business to business domain. Salesforce is a CRM tool for sales executives providing features like customer. Google, Microsoft, Amazon, everyone provides it. Since the cloud vendors provide services on the web, these are available from any location. So that is the difference between the old way of doing it and the new way of doing it. Cloud computing can be ordered online without detailed formal contracts. Cloud computing provides a level playing field. An example of Mozy Online Storage provides online backup. Now everyone does it. So, sort of trying to wrap this up. So now today cloud is very prevalent. Everyone is using the clouds. I mean, may not be everyone, but a lot of people are using the clouds. So there are different types of clouds. Here is a list. Public clouds. Public clouds means anybody can use that cloud and put your data on that, and it's accessible to everyone. You also have private clouds, means these are very specific clouds set up for specific purposes. So for example, I know US Department of Defense, Air Force has its own cloud, military has its own cloud, and Space Force, they are private clouds that cannot be accessed by anybody else for privacy, security, various reasons. And you have hybrid clouds. You can have hybrid clouds, and interestingly, there are community clouds. So for example, many states, state of California has its own cloud. So everything that is done, all the paperwork or even digital work, everything that is done in the state of California is on their cloud, which can be accessed from anywhere. So cloud, yeah, I'm sure even here perhaps NIC here provides such kind of capability. So you may have something like that here as well. So this is becoming very common, and you can see that here. So services, you can provide infrastructure as a service, you can provide platform as a service, you can provide software as a service. I just have a line on one of these. So today there is no limit to what you can provide as a service in a cloud. So cloud is kind of an abstraction. It has certain characteristics. As long as those characteristics are there, you can use it and do that. So to summarize, essentially a paradigm or a model where capital equipment, management and maintenance can be rented instead of owning on a need basis. So this is also to some extent outsourcing does that in a way, but for a different purpose, for a different reason. For raw commodities such as CPU, storage and bandwidth, this is straightforward. In fact, most hosting websites use a similar model, but they also provide different levels of development tools. You can ask for DBMS on that. You can ask for MATLAB. You can ask for any software that you want that can be provided. However, it would be very useful if you can also support a transparent programming paradigm to use these resources effectively. So this will lead to, in a couple of lectures, our MapReduce paradigm. Okay, I think this, oops. Okay, maybe this is the end. So I'm going to stop here today, and then I think we'll break for lunch, and then there is one more hour of lecture.
So in these sessions, I will cover scaling deep learning to graphs with respect to convolutional neural network features and GIAN, that is graph neural network structures. So these are the basic contents that I will cover in this lecture. First is the scalability crisis, that is big data in this real world. As Professor Chakravarti in the morning session has very well explained about the big data's problem. So from that we will start. And as my field is just related to the image processing, so I will just divert big data problems in the field of image processing. So for that we need some basis, for example neural networks, then convolutional neural networks, then how to just bridge from pixels, that is an image is represented with the help of pixels. Now how to transfer these pixels to the topology. Topology means in the form of graphs. Then we will cover simple graph neural network foundations, and then with some future directions in which we can use these technologies. So first I will start from the same 4 V's of big data. In morning lecture, Professor Chakravarti has very well explained what are these 4 V's. That is volume, variety, velocity and veracity. So now in this lecture we will move from volume to variety. Volume to variety means we will try to handle high dimensional complex data, that is today's real world data. If we see in today's world, everything is in the form of images and videos. So we will just try to cover this variety of data, and as we have seen that in yesterday, structured DBMSs were used, that is proper index databases were used, but in today's world we have unstructured data. Unstructured data means unstructured data means videos, and as we know, videos are just, what are videos? These are just a sequence of images, sequence of image frames, and an image is represented with the help of a matrix. So videos are also stored in the form of matrices. And if we say in terms of videos, then we say this is just, you can say, problem of big data. That is just, if we say just one image means so many number of pixels. And if we say video is a sequence of images. So then that means we need so much storage space as well as we need simultaneous processing to process this sequence of frames. So here scalability mandate is just, we say we should have architectures that must scale to complexity, not just the size. So just we can say transforming raw pixels into actionable plans. If we say in the real world, where we are using video cameras, so just we can say enterprises are drowning in photos, videos and sensor feeds. Unstructured data is impossible to index or search manually. So we want AI shift, that is just we use AI to read and tag visual data automatically. So just then that means we want to identify critical patterns in the videos that a human eye can miss. So we want decision engines, that is turning these cluttered pixels into the real-time business instructions, that is moving from the passive storage to the active intelligence. Then that means here just we do not want to store only the data, as Professor Chakrabarti in last lectures already explained. Then storage of data is not sufficient. When we store the data, after that we want to analyze that data. We want to retrieve some meaningful information from that data. Similarly, in today's world we are storing a number of videos, but if we do not want to extract the meaningful information from that video, then that storing of videos is useless. So then that means we want just active intelligence. Active intelligence means just to process these videos and interpret those videos. In coming slides we will discuss some emerging areas in which we can do the research using these convolutional neural network and the graph neural network. So we can say visual intelligence is about automating the understanding of complex environments, not just collecting more data. Now from here we will start our just the basics of image processing and basics of videos, that is visualizing an image as a mathematical point. All who have studied image processing, they know how to store the image in the system. Then that means to store an image in the system, we just do the sampling. Sampling means just we divide our image into the spatial coordinates. So after that we also do the process of quantization. What is quantization? Just you can say to store the intensity values. So we can say every image is a grid of numbers. So in case of grayscale images, we have just one matrix, that is only we store the grayscale values. But if we have colored image, then we have three matrices. We have to store three components. One is the red component, green component and the blue component. So just we can say the images are actually stored in the form of matrices. That is 2D structure, two-dimensional arrays. So when we want to process these two-dimensional arrays, we have to flatten them. Flatten them means we have to just store them in the form of a vector. So here we can see if we have a 224 into 224 image, then that means when we flatten it, we will get around 50,000 dimension. So in big data, an image is a single point sitting in a 50,000 dimensional space. Then that means, for example, if we want to do some image similarity problem, we want to search similar images, then that means we have to search an image related to a particular image from a big set of images. Now each image is just a single point in the 50. If each image is represented with the help of 224 into 224, then that means in the 50,000 dimension, every image is just a single point. Then that means we have to deal with so much data. So how to deal with such type of data? For this, just we can say neural networks come into the picture. So as we say, our brain, a human intelligence, if we say human intelligence is mostly devoted to the vision problem. 90% of the brain is just devoted to the vision. So what is in our brain? Just in the form of, just we can say, we have neurons, just we process signals. Similarly, this neural network is a simulation of, just you can say, human brain. So brain does not read files, it processes the electrical pulses. So similarly, in case of artificial intelligence, we develop artificial neural network, that is artificial neurons. So we map 50,000 pixels to the artificial neurons. So just you can see here, that is in this case, just you can see in this case, this is a just example of a neural network. Now see, coming to the next slide. See here. Here when we say an image is fed to a neural network, we can see that is just these 256 into 256 pixels are just converted to the one-dimensional vector, and then these are given to a neural network. Then these are given to a neural network. Now this neural network processes these pixel values and gives some probability that what type of an image it is. So just you can see, neural network is just a fully connected neural network. Neural network, if we say simple neural network, this is a fully connected neural network. So here we can see this thing, that is this green. What are these green symbols? These are the actual pixel values of an image. And now these pixel values are processed with the help of these hidden layers. And after processing, some probability is given, that is what type of image it is. What is the probability that this image is of a cat, this image is of a dog? What is the probability? So how this neural network actually learns? Neural network learns with the help of the back propagation algorithm. Then that means this is just a kind of supervised learning. This is just a kind of supervised learning, that is training samples are passed through the network and the output obtained from the network is compared with the actual output. If an error is there, then that means what is that error? That error is called, in terms of neural network, that is loss. So that loss is back propagated through the neural network. So our main aim is just to minimize this loss.
We have one doubt from our online viewer. So he's asking, like, if we use AI for tagging, does it mean we have, or we are compensating for lack of domain knowledge?
Yes?
The question is, if we use AI for tagging, does it mean we lack domain knowledge? Is that why AI is being used?
No, we can say we can do with the help of simple machine learning models also, but if we use artificial intelligence, then that means just we get similar type of features, and similar type of features are matched with the, just you can say, your training data. So with the help of that, we can just tag the images. So the error is used to change the weight of the neurons so that error decreases gradually. training a network is just training to minimize its loss. What is loss? Loss is just, we can say, error. What is loss? It is just an error. So our purpose is just to minimize that error. Our purpose is just to minimize that error. So in case of neural network, we do not say that we always go with the accuracy. Our aim is also to minimize this loss. So this is done using the back propagation algorithm. So here we can see in the figure, these are the image features, and here these features are passed to the neural network, and here whatever the output is there, if that output does not match with the actual output, some error is there, that error is back propagated, and according to that error, these weights are updated. So training a neural network means just we are getting the exact values of these weights. Our main aim is to just getting the values of these weights. So just we can say, if we say a simple image is given as input to the neural network, then that means here so many number of layers are there. So many number of layers are there, then that means there are just we can say a number of parameters. For example here 1000 neurons, and if we have just this image, then that means we have 50 million parameters. 50 million parameter means again a lot of data. So then that means we have to deal with such data. How to handle this data and how to just we can say get the actual values or just correct values of these weights or parameters. So just we can say that is here our aim is just to get the actual values of these parameters. So we need a lot of training data. We need a lot of training data. So just we can say if we do not have these, so if we our main aims to have less number of weights. You have listened these terms, that is the lightweight models. Lightweight models means just we can say if the number of parameters are less, we develop such a neural network which has less number of parameters. Then that means less number of parameter means we have to train the neural network so that we have to get less number of parameters exact values. Then that means our model is light, we need less training data. So just we can say in case of simple fully connected neural network, if we have want to process the images, then so many parameters is there and model memorize specific noise rather than general features. What does it mean? See here again this figure, that is if we say what are these green x1 to xn, these are the pixel values of the image, and how these values are just we have converted our two-dimensional image to the 1D image. Now see, every value is connected to the every neuron in the next layer. So if we have 2D image and the value in the upper left corner will also have some role to the value in the lower left corner, then that means spatial relationship has been lost in case of simple neural network. That is not requirement in case of our images. So just we can say in case of standard neural networks, these are translation variant. These are not translation invariant. What does it mean? That is if we have an image and in that image we have some picture of dog or cat, and in the next picture again we have dog or cat, but the position of the dog or cat just is not the same. Then we can say the input to this neural network will totally change. So then that means these simply neural networks are not translation invariant. These are translation variant. So that is why we need some other type of networks, that is convolutional neural network. So this is again the same problem that I have explained in the last slide. That is just in fully connected layer, every input pixel talks to every hidden neuron. So just this is the 2D image. 2D image has been converted to the one-dimensional vector, and this one-dimensional vector is given as input to the every neuron. So just we can say this pixel in the image also plays some role for this pixel in the image, because every pixel value is connected to the every neuron. That is not our requirement in case of images. So this is the need of convolutional neural network. So here just we transition from the just you can say simple intelligence, or you can say to the spatial intelligence. Spatial intelligence means just here we can see, rather than converting 2D image into the 1D vector, we perform the local receptive fields, that is the convolution operation, with the help of some kernels. So here, what is that operation? We have some filters or kernels having some weights. So now these filters are processed with the help of these images. So neuron should only see a small window. See this. Now here we are using as 3 into 3 filter. So 3 into 3 filter means here we will use just 3 into 3 receptive field. So an object is just a collection of local relationship. By ignoring distant pixels, we reduce parameters by 99.9%. So just you can see in the last image, every pixel is connected to the every neuron. But here just we have local receptive fields. And again these fields share the weights. Or these field kernels, these filters share the weights. So number of weights are reduced. So just we can say intelligence is not about seeing everything, it is about knowing where to look and who your neighbors are. So just this is just we can say shifting from the simple neural network to the convolutional neural network. That is in case of dense wave we have global connectivity, and in case of spatial we have local connectivity. In case of simple neural network, every pixel is independent. Here pixel form the structures. These phase at the high resolution, this scales to the 4K and beyond. So this is just a similar to reading a book, letter by letter, just same pixel by pixel, and here reading a book word by word. Then that means spatial intelligence is there. So we solve this parameter explosion by teaching AI to see like a human rather than reading a matrix like a computer. So this is how CNN evolves. So this is the next topic that I will cover, convolutional neural network. So convolutional neural network come into the picture for processing images with the help of deep learning. So here we see every simple convolutional neural network is just a combination of so many layers, because it is a deep learning. A number of layers are there. Convolution layers are there, max pool layers are there, fully connected layers are there. So in the last we see here, in the last again we have fully connected neural network. But initially we have convolution operations. So what are these convolution operations? See here, again same. A specialized architecture that processes data with a grid-like topology. It transforms raw data into a probability vector representing the class codes. So just you can see local connectivity. Local connectivity means unlike dense layers, CNN neurons only look at the nearby pixels, as I have explained earlier. So mimics the human visual system, detects simple edges before the complex objects. So eliminates global noise and focus on the structural patterns. Global noise means that is now this pixel may not play a role in whenever we deal with this pixel, depending upon the kernel size. So this is the example how kernel behaves, or how convolution takes place in case of images. See, this is just we can say a 5 into 5 image is there, and this is the 3 into 3 kernel is there. So instead of unique weights for every pixel, we reuse a small kernel across the entire image. We use a small kernel. Now see, this is an example of a kernel. For, let us suppose the kernel has initial weights 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. Now how this behaves? First, this kernel is placed here. Now see here, every corresponding pixel is multiplied with the kernel value. So 7 into 1 plus 4 into 1 plus 3 into 1 plus 2 into 0 plus 5 into 0 plus so on, we get here value 6. Similarly, after that stride operation is there, stride here is 1. Again the same kernel is placed on the, just by sliding one pixel. Same kernel is placed, then that means same weights have been shared. So again we can see here, this convolution operation is translation invariance. A vertical edge is the same feature regardless of its coordinates. Because if in this image, when we place this kernel, similar type of values will be there, and if we translate an object from here to here, again somewhere we will get the similar type of values. So a billion pixel problem is solved using just with the 9 weights. So in case of fully connected neural network, you have so many parameters, but here we have reduced a number of parameters. So filters automatically learn to sharpen, blur or detect edges. So this is the way how kernel. Now next is, as in the last slide we have discussed that stride is 1. But if we want to reduce more data, and then rather than applying stride 1, we can apply more than one stride also. So we can have just stride 2 plus also, like this. So now this is all about when we do convolution operation on the grayscale images. But in case of colored images, in case of colored images, we can say same filter is applied to all the channels, that is RGB, red, green and blue. Same filter is applied, similar type of convolution operation is done, that is corresponding pixel values are multiplied with the kernel values, and then summation is done with the red channel, with the green channel and with the blue channel. And after that we summation. Again apply the summation operation. So just we can see here, if we have here the image that is 32 into 32 into 3, then after convolving we have 30 into 30 into 1 with 3 into 3 filter. As we have seen in the last slide, after applying the convolution operation, if we do not have zero padding or any other type of padding, then the size of the image reduces after the convolution operation. And again we can see here the depth is 3, but here depth is 1, because all the components have been added, that is red, green and blue. But in case of deep learning, we rather than having with single kernel, we have a number of kernels. For example, here we have used 32 kernels. So when we have 32 kernels, then that means here 32 into 32 into 3 images there, here some padding also has been used. Then for each kernel we will get a different type of output. So weights per filter will be 3 into 3 into 3 channels, that is 27 weights. Total weights per layer is this, and output and activation map of size this. We will get this. Now see, after this convolution operation, these stacked feature maps are passed to the pooling layer. So what is pooling layer? Again it is used to simplify the data. That is again to reduce the data. So just we can see here pooling. Pooling means we can do max pool, we can do average pool, or we can do just min pool. Any type of pooling operation can be done. So here once applied immediately after convolution, pooling reduces the spatial size, that is width into height of the feature map, while preserving its depth. So parameter reduction, fewer pixel means fewer computation in the subsequent layers, Then that means after pooling operation we have reduced the size, then that means data has been reduced. So data has been reduced means fewer computations will be there. So fighting overfitting, by discarding precise pixel location, the model learns to be less sensitive to the minor noise. Spatial intelligence, it shifts the focus from where exactly is this pixel to is this feature present in the area. So this is just, we can say here, size of the just we can say output of the convolution layer is like this. After the pooling layer, size of the image has been reduced. So this is the way just how pool works. For example, here just we have applied max pool with 2 into 2 filter. So when 2 into 2 filter is placed here, max pool is there, maximum value here it is from 7 to 4 and 5 is 7. So it becomes 7 here. Again, when to this portion 5 to 4 7, 7 is the maximum here, 7 is there, 3 3 6 4, 6 is there, 4 2 8 6, 8 is there. So this is the way how max pool performs the operation. Now see, from here we see how CNN learns the features. Now see this image, this particular image. Here we see this image is a particular animal, but when the convolution operation is performed here, this convolution operation will map to just this pixel, this small square here, then this square, then this whole area. When convolution operation is performed here, this area will just come down to only this area. So in the first layer, just you can see the square marked 1 is obtained from the area in the image where the leaves are painted. In the second layer, the square marked 2 is obtained from the bigger square in layer 1. So just you can see here 2. This 2 is obtained from this. Just you can see this bigger square. Now this bigger square, if we see this from where this bigger square is there, this square is from this portion, this square is from this portion. Then that means here we can say the initial layers are looking at the smaller regions of the image, and thus they can only learn simple features like edges and corners. That is, the initial layers only learn, just you can see, look at the smaller regions, and they learn only the simple features like edges and corners. As we go deeper into the network, the neurons get information from larger parts of the image and from various other neurons. Thus, neurons at the later layers can learn more complicated features like eyes, legs, etc. Then, this is the way how CNN works on the images. So, at last, when we want to recognize after number of convolution and pooling layers, we have to flatten the output again into a single dimensional. Then that means again we have to just flatten that output vector, and these output vectors can be again further connected to a fully connected neural network. Then that means till now we have extracted the features of the image, and after that these features can be given as input to a fully connected neural network for the classification purpose. So just you can say fully connected neural networks cannot interpret 3D grids. They require one-dimensional arrays. So every pixel in the final feature map represents a complex high-level feature. And while spatial coordinates are simplified, the strength of the detected features is preserved for the classifier. So just we can say after a number of convolution and pooling layers, the output is converted to a 1D vector. Just you can see here. Here we have an image of a digit 2, a number of, just you can say, convolution layer, pooling layers is there, and after that this, just you can say, spatial relationship is converted into, in the form of which is 3D matrix, that is converted into a 1D vector which is passed to the fully connected neural network, and after that we have class probabilities, and again we can say final interpretation is just final layer uses the softmax function to output class scores, and the index with the highest value is the model's prediction. So we can say what is the model's prediction, that the image probability of the image being true is the 98%. So CNN automate the understanding of complex environment by turning cluttered pixels into the actionable plan. Now again, if we see here, we have just moved from the neural network to the convolutional neural network. But again, for convolutional neural network, we need a lot of data. But for some particular problems, we may not have some data. For example, for any medical problem, we may not have just, you can say, data of the persons having a particular disease. From where to get that data? So for that, the concept of transfer learning is there. Then that means if we want to deal with the problems where we have not too much data, we can have the concept of transfer learning. What is transfer learning? Just again similar to our human intelligence. For example, sometimes we have seen some just a picture of fruit, but we do not what type of fruit it is. But we match that this seems like that. Then that means our brain is trained with some similar type of problems, and we recognize the fruit which we have not seen earlier with the knowledge that we have gained from our previous. So that is again here used in the concept of deep learning, that is concept of transfer learning. Here we can see in case of traditional learning, if we want to recognize these oval shapes, these triangles, these just diamond shapes, then for different tasks we have different type of models. But in case of transfer learning, if we have trained our model using ovals and just triangles, we can apply same knowledge to identify these diamond shapes. So just we can say training a deep CNN from scratch requires massive data and compute. Transfer learning makes data science capable of reusing the feature vector. Then that means we train our model on some other type of problem, and that trained model can be used to solve some other type of problem. So this is the concept of transfer learning. So just you can say, instead of random initialization, we transfer the weights from a model pre-trained on a large data set. For example, a number of pre-trained models are there in the literature. You have listened the terms BGG16, ResNet, all these are the pre-trained models. These pre-trained models are already trained on the data set, that is the ImageNet data set. What is this data set? This data set is having the pictures of just different objects of 1,000 classes. So every model is trained on that data set. Now see here, we keep the layers. We keep the layers that detect edges and textures. You can see here. Here we have just some source data set, some convolution layers, and then some dense layers are there. And here just we can say this model is trained only to recognize the images of the dog. Now see, same knowledge is used to recognize the images of dogs and cats. So here what we have done, just you can see here we have frozen these layers and we have trained our model only for the last layers. Then that means the weights for these layers are already we have got from the previous knowledge. So just you can say, now with the help of this transfer learning, we have achieved this scalability. How scalability? Just training 1% of the parameter is 100 times faster than the original. Because in case of traditional learning, we have to learn so many parameters. So many parameters means we need so much data. So, but in case of transfer learning, we have freeze some layers. And freeze some layers, now we have to train only some of the layers, the last layers. And only the last layer means less number of parameters. Less number of parameters means training is fast. So, here in case of transfer learning, we need 100 of images instead of millions. Now, next portion is just here what we have covered till now. We have covered just images. What are the images? How images are processed using the computers. Then we have just learned about the neural networks. Then for processing images, why we need convolutional neural networks. Now next is what is the problems that CNN face. What are the problems that CNN face? Now see, CNN are the local thinkers. They process small 3 into 3 squares. To understand a relationship between distant objects, they must become incredibly deep. See this picture. Here, a person is, just you can see, having 2 phones in each hand. So, when a CNN works, how CNN will work? CNN will work just like this, small receptive field, 3 into 3 filters. So, just to get the information, that is just the action, that is a CNN identifies the phone, but struggle to understand the action, that the person is talking on the phone as well as the person is having another phone in other hand. So then that means this is the problem in case of convolutional neural network, because convolutional neural network deal with only the small receptive fields. So from here, just we can see one more problem. Just you can see, if we have just a traffic control system, we have installed the cameras on in the city, then how to see the traffic. Now when we process the video, again what is a video? It is a sequence of frames. Sequence of frame means it is again, each frame is consists of pixels. So then that means to analyze that video, the system has to process each pixel. So then that means even the empty roads or the roads with the car, the system has to deal with both type of videos in the same way. So this is the problem just that we have faced with the CNN. So here the concept of graph neural network is there. That is intelligence over pixels. That is just we can say from pixels to the nodes. Pixels to the nodes. We strip away the pixels and keep only the nodes and edges. So in case of just we can say scenic graph, we will shift just that is we will have just the objects, that is a person and the phone and the relationship between them. So focus is 100% on the semantic relationship. Again in case of smart city graphs, we will have just different type of nodes, that is what type of objects can be there on the roads. There can be cars, there can be cycles, and what are the relationship between these. So we have only now these 70 nodes versus 8 million pixels. So just you can see, in case of videos, whenever we have to deal with or we want to process an image in which we want to understand the image, semantic relationship in the image having different objects, so we have to shift from the CNN to the GIAN. So we can see what is CNN. This is just a magnifying glass. And what is GIAN? It is a network diagram. Here it is deal with the pixels and here it deal with the relationship. And CNN only deal with what is present in the picture. Is this a car? and GNN deals with the action. Will this car cause an accident? So just you can see here, because we have to process every pixel, the cost in case of CNN is high, but here we have to deal only with the nodes and edges, so the cost processing is low. So just we can see this is the way how we convert from, or how we shift from CNN to the GNN. So we can see in case of CNN we have the concept of Euclidean distance. That is, every pixel is connected or having 8 neighbors. Every pixel is having 8 neighbors, left, right, up and down and diagonal. But so this is a fixed structure and uniform distance is there. But in case of graph neural network, topological graph, we do not have fixed structure. We have just the concept of graph. Each node is connected to some other nodes. For example, if we say the real world example, in case of Facebook, you have some friends. So how this, just you can say, all things are maintained in case of Facebook in the form of graphs. You have a friend, you are having some friends, so you are connected with your friend. And your friend now are having some other friends, they are connected with those. So then that means this whole social network is represented with the help of graph. So just we can see here GCN, that is graph neural network. So again, just we can say in case of graph, what we store, each node can represent a pixel or each node can represent a combination of pixels. Combination of a pixel means just a superpixel, a cluster of similar pixels. For example, you have identified that this is a there is an object in the picture, that is image. You can there is an object in the picture that is of picture of cat. Now you can represent that cat as a node. So then that means nodes in the graph can be a pixel or can be a superpixel. That is a collection of pixels depending upon your problem. And each node has a feature vector. Each node has a feature vector. What are these feature vectors? These can be the color, its intensity, its texture, its geometric features, that is XY coordinates, then semantic information, that is that information that it has learned from the previous layers. So just we can see here an example. This is a graph having 5 nodes. So here I think all of you know the concept of adjacency matrix that is used in case of data structures. How graph is represented using the adjacency matrix. So just you can see here graph is there of 5 nodes. So 5 into 5 adjacency matrix is there. So A is connected to E. So only here 1 is present. E is connected to every node. Just here, so here we can see for every node it has 1. So again, this is the degree matrix, just number of incoming and outgoing edges. Now this is the feature vector. Now each node can have its own features. So these features are for each node, these are again stored in the form of a matrix. That is, each node has its own features. So just you can say a GNN does not know its own color, it talks to its neighbor to understand the context. So like a person at a party, a node's identity is shaped by the people it talks to. Then that means in case of GNN, whenever we want to identify a particular node, the node is not known only by seeing it. It also known by seeing its relationship to its neighbors. So the goal is to create a rich description of every point based on its relationship. So this is the technique how GNN works, just by passing the messages. Just you can see here that for every node a message is passed from its neighboring node, and these messages are, summation of these messages is done here, and then whatever the action that is matched with the actual output, and if the actual output does not match with the your computed output, then that means some loss is there. If some loss is there, again back propagation is done. So graph neural network behaves in the same way as the simple neural network. So just you can say send every node prepares a message about itself. A node collects all messages from its neighbors. The node combines its old info with the new neighborhood gossip to update its state. So multi-hop effect is there. That is layer 1, you know about your friends. Layer 2, you now know about your friends of friends. Then that means again this graph neural network has a number of layers. So depending upon your requirement, here is some example how this message passing works in case of graph neural network. Now see, let us suppose we have an image. Here image is of, just we can say, our environment having some clouds and the sky. Now see, what are if the initial values of the pixel, that is actual cloud, that is 0.51, that these are the intensity values of feature, we can say feature values, and its neighbor is having 0.48, that is the neighbor of the cloud, and the pixel values of the actual sky is 0.45, and its neighbor is 0.47. Now see, the gap between x2 and x3 is only of 0.01. So a simple threshold 0.5 would wrongly put x2 in the sky category. So see here, the difference between these two is only 0.1. So x2 is actually cloud neighbor. But because the difference is too less, we can say x2 is also sky. But how this problem is solved? Using the graph topology. Now see, in case of graphs, we do not let node 2 decide its identity alone. We use the adjacency matrix to define who it should listen to. Then that means we do not just only say that node 2 will decide its identity. Its identity will be decided by its neighbors also, its friends also. So friends, if the same reason is there, then we have just connected node 1 and node 2 with weight 1, and different reason node 2 and 3 are connected with weight 0.1. So by setting the weight to 0.1, we tell the artificial intelligence system, listen to your friend but mostly ignore the stranger across the border. So here we can see how message passing works. Now we compute the new value. We compute the new value. Here new value is just, we can see how it is computed. 0.48 into 1. 0.48 into 1 means its own weight. Plus 0.51 into 1, that is friend. Plus 0.47 into 0.1, that is stranger. So for this, when we have computed new value for the node 2, it comes to 1.037. And for similarly, when we have calculated for the node 3, it is 0.968. Now see, from here, we can see before graph GNN, node 2 has value 0.48, node 3 was having value 0.47. So the gap is only of 0.01. So then that means this gap is just too less. So just we can say we can wrongly identify node 2. But after applying graph neural network, the difference is of 0.069. So just we can say GNN use the topology to pull pixels towards their true group. Then that means now it actually belongs to its actual class. So again, here we can see in this model we have used just default weights, that is 1 and 0.1, but when we train graph neural network, we actually train these parameters. We actually train these, we actually get these weights by training the neural network. So same way we calculate the loss, and that loss is back propagated, and according to the loss, weights are updated. So this is again gradient back propagation and how to update. So again, in case of graph neural network, we have the concept of pooling layer, that is we can combine several nodes to a single node. So pooling can be done in case of graph. So in last we can see, in case of actual video processing or image processing, we do not have only the concept of CNN or only the concept of GNN. We have to use both. For CNN, just to detect the objects, and graph neural network just to detect the action. So just you can say CNN training is learns to extract the better pixels, and GNN training is learn to build better edges. So just you can say, in case of CNN, object detection and feature extraction is done, and in case of GNN, reasoning is done, that is relational modeling and prediction is done. So again, in summary, just we can say CNN reduces high dimensional raw pixels into the compact meaningful feature vectors, and topology for reasoning moving beyond the grid to a flexible graph defining entity interactions. So again, now we will discuss the application areas where these concept of CNN and GCN can be used in combination. For example, in case of smart farming, farms are too big to check every plant by hand. So simple logic, drone takes photos, CNN looks at each leaf to see if it is having some disease. GNN connects all the plants in a map to see how a disease is spreading and or where the soil is dry. Then that means CNN deals with just what and GNN deals with how and what to do. Action plan. So you only water or spray medicine exactly where the graph says it is needed. So same again, city planning and safety. When a bridge breaks, how does it affect the whole city? For example, after any disaster, after floods or anything, whenever any disaster is there in any city, some bridges breaks. So which bridge has the most effect in the city? So satellite take pictures of the city. CNN spots cracks or damage. GNN treats the city like a giant web of roads and bridges, just connectivity of the city. So result, it tells emergency workers which road is the most important to fix first to know the city, to keep the city moving. So this is just you can say how the combination of CNN and GNN is actually can be used to solve the real world problems. Similarly, fast warehouses, robots can get stuck or take long pass in the big warehouses. Cameras watch the warehouse floor. CNN identifies the boxes and robots. GNN calculates the traffic on the map. And action, robots find the shortest path and never crash and make deliveries fast. Similarly, reading documents, just computers often get confused by complex forms. So CN sees the text blocks and stamps, GNN understand the number at the bottom right is the total price. So computers can read and sort millions of bills perfectly in the seconds. Then again, power grid protection. One small wire failure can cause a whole city blackout. Then thermal cameras look for hot spot on power lines. The CNN task, GNN map how one wire is connected to the rest of the grid. And engineer fix the most critical wires before they break, keeping the lights on. Similarly, robots and humans, that is robots in factories can be dangerous if they hit a human. So Steve sensor watch the worker, the CN identifies human's arm or leg. GNN predicts the social space, it calculates where the human will move next. Robot automatically slows down or moves away so humans and robots can work side by side safely. So just we can say processing every pixel in 4K or 8K video is computationally unsustainable. So by focusing only on the relevant nodes, we reduce the computational footprint by 90%. So topological models allow high-end vision to scale to the low-power edge devices. Scaling is not just about the size, it is about making AI smarter and more sustainable. So this is the conclusion, that is visual reasoning in today's ultimate real-world scalable data challenge. Combining CNN features with GNN structures is the key to fast, scalable and intelligent research. So in this lecture I have tried to explain, that is, in case of data, in today's world, main concern is with the visual data. So how to just handle this data with the help of deep learning techniques. This is all about this lecture. Thank you.